Hi everyone, this is Design of Machine Elements 1, tutorial number 3 on chapter 2, Static Failure Theories. So in this problem, we have given a round shaft which is subjected to a torque of 565 Newton meter and a bending moment of 250 Newton meter. And the shaft is made from AISI 1010 steel. And for a safety factor of 2, we are required to find out the diameter of the shaft, which is enough for carrying this 565 Newton millimeter torque and bending moment of 250 Newton meter without any failure. So we will find out the diameter of the shaft using MSS theory, DE theory, and MNS theory. Remember that in the previous example, the given information were on the first problem, we were given induced stresses or working stresses. And in the second problem, we have solved a factor of safety for when principal stresses were given. So this third problem is a different kind, where we are required to find out the size of the machine component given a safety factor and a specific material selected for that purpose. So as usual, to solve this problem, the solution always should start with extraction of the given information. So torque is given to be 565 Newton meter. Always convert Newton meter to Newton millimeter for the units to be consistent. So 565 Newton meter means it is 565 times 10 raised to 3 Newton millimeter. And bending moment is 250 Newton meter. For conversion to Newton millimeter, it is equal to 250 times 10 raised to Newton millimeter. Factor of safety is specified to be 2. And for this AISI 1010 steel from mechanical property table, we can read for the yield strength, and it is equivalent to 180 megapascal. So 1 megapascal is 1 Newton per millimeter square. So we need to convert this again to Newton per millimeter square. So the units all are going to be consistent in this way. So the yield strength is under 80 Newton per millimeter square. Now, having this data, we will determine the diameter of the shaft using MSS, DE, and MNS theory. So this is a free body diagram for the shaft. The shaft is subjected to torque along x direction. So don't forget, torque causes shear stress and bending moment along this direction. Bending moment induces normal stress, or we call it bending stress. So the equation to calculate for shear stress due to the torsion is given by this expression. So shear stress along xy direction is equivalent to torque multiplied by r divided by j. R is the distance of the point that you consider from the neutral axis. So R is measured from the neutral axis. The neutral axis is an axis where stress is supposed to be 0. So R means it is the point that you consider from that neutral axis. Don't forget always, our design bases on maximum shear stress or maximum stresses. So this shear stress is going to be maximum when R is maximum. So R is maximum when it is equal to D over 2. So substitution of D over 2 in terms of R, and J is polar moment of inertia for round sections. It is given by pi d raised to 4 over 32. So if you substitute and solve for simplify the expression, you will end up with shear stress equal to 16t divided by pi d cubed. This is a famous expression for finding shear stress in a bar subjected to, in a round bar subjected to twisting moment. T is already given, it is 565 times 10 raised to 3. So if you substitute and simplify, you will get the shear stress to be this value. Okay, now we are done with the shear stress induced in the bar due to twisting. Now we need to find out the normal stress subjected on the bar due to the bending moment. Find out that we need to use this famous flexure equation. We call this one flexure equation. And normal stress is equivalent to M multiplied by Y divided by I. So this is normal stress, or you can call it bending stress. So always bending stress causes a normal stress. And Y is again the distance to the point that is considered from the neutral axis. Neutral axis is found on the center of the shaft. And always our design based on maximum stresses. So this sigma x is maximum. This sigma x is maximum when y is maximum. So y is maximum when it is equal to d over 2, which is at the outer periphery of the shaft. So shear stress and normal stress all are maximum on the outer periphery, of the shaft, or on the outer surface of the shaft. So if you substitute these values, well, I is the moment of inertia of the shaft. So for round sections, it is given by pi d raised to 4 over 64. So now if you simplify this expression, then you get 32m divided by pi d cubed. This is the famous equation for finding normal stress on a round bar which is subjected to bending moment. If you substitute now in terms of m, the given value, which is 250 times 10 raised to 3, then you get expression of normal stress or bending stress in terms of the diameter of the shaft. This is the plane stress state where you have stress along x direction, normal stress along x direction, and shear stress along xy direction. Now we are going to apply maximum shear stress theory to find out the diameter of the shaft. So as usual, maximum shear stress is expressed in terms of principal stresses or applied stresses. So in this case, then this equation will be appropriate to use because the stresses that we have are all applied stresses or working stresses. So you need to substitute the values that we have got earlier, means these values, the shear stress value along xy and normal stress along x direction are found to be these values from our previous analysis. Now, if you substitute these values into this equation, then you'll get this expression. Don't forget, SY is already known. It is equal to 180 megapascal or 180 Newton per millimeter square. If you substitute it here, then the only unknown value will be the diameter of the shaft. So if you solve for D from this equation, then you get this expression. So calculating the value of D, you'll get it to be 41.21 millimeter. This is diameter of the shaft calculated using maximum shear stress theory. Now we repeat the same analysis for I'm using distortion energy theory. Don't forget always, distortion energy also can be expressed in terms of principal stresses, and also it can be expressed using applied stresses. Here we have, since we have applied stresses, we apply this expression, or we use this expression to find out the diameter of the shaft. Now look here, sigma y is 0 because we don't have a load acting along the y direction. There is no load causing sigma y. So sigma y here automatically will be 0. So sigma x, you already know it to be this one. And tau xy, you already know it to be this one. So you substitute these expressions. So from this, the only unknown value will be here again, the value of the diameter of the shaft. So if you calculate the diameter of the shaft from this expression, then you get it to be 39.63 millimeter. This is the diameter of the shaft calculated using distortion energy theory. Here again, remember that the sizes that we calculate using DE theory are always less than from the size that we calculate for using the maximum shear stress theory. So in this case, the diameter of the shaft is found to be 39.63, which is less than from the value that we have calculated using MSS value. Okay, we can also use, at least for comparison purpose, so MNS theory is only applicable for brittle materials. Let's see what will happen if you use MNS theory. Okay, MNS theory states that failure occurs whenever one of the principal stress exceeds the yield strengths of the material. This is the general expression of MNS theory. So here in this case now, we need to look for, or we need to find out principal stresses, because the equation is only expressed, this equation is only expressed in terms of principal stress. The principal stress can be calculated using this expression, as we have seen in our lecture. So here, sigma y is 0, sigma y is 0. The other values we do already have, sigma x, tau xy, and also sy is known. So if you substitute the values, which are these values, if you substitute these values into this expression, then if you solve for d, if you solve for d, if you solve for d from this expression, then you get d to be this value, which is 29.08. So you see that this MNS theory is somehow biased to use for the case of uh, ductile material. So that's why we don't use it uh, for ductile material, because it doesn't give us exact prediction of failure. So you see that this is at least less by 10, the size less than by 10 millimeter from earlier values. So this one is not, or this theory is not totally recommended to use for brittle materials. Okay, this is how we actually calculate sizes. Whenever we have given factor of safety, material, and load applied, this is how we solve for the size of any given machine component. Okay, this is going to be the end of the tutorial. Okay, thank you very much.